Swayam Prabha. Digital India. Educated India.
In an earlier lecture, we have already mentioned that there are two types of problems in kinematics, namely kinematic analysis and kinematic synthesis. In kinematic analysis, we determine the relative motion characteristics of a given mechanism. From today's lecture, we shall start discussion on this topic of kinematic analysis. Broadly, we can classify the kinematic analysis problems into three headings, namely displacement analysis, velocity analysis, and acceleration analysis. For all these three types of problems, that is displacement analysis, velocity analysis, and acceleration analysis, we can use either a graphical method or an analytical method. In today's lecture, we discuss only the graphical method, and that too only of displacement analysis. Later on, we shall take up velocity analysis and acceleration analysis. Let us see what do we mean by displacement analysis of a mechanism. If we are given the kinematic dimensions and the position or movement of the input link, then we should be able to determine the position or movement of all other links by this displacement analysis. In the graphical method, first we draw the kinematic diagram of the mechanism to a suitable scale, and then the desired unknown quantities are determined through suitable geometrical constructions and calculations. We shall demonstrate this graphical method through a series of examples. However, before going into the details of each and every example, let me list the main points that one should remember while using graphical method of displacement analysis. So, the main points are, first of all, we must remember that the configuration of a rigid body in plane motion is completely defined by the location of any 2 points on it. That means, if we know the location of any two arbitrary points of a rigid body in plane motion, then we know the location of all other points on that rigid body. The second point is, as we will see when we solve the examples, that very often we will need to draw two circles which are intersecting, or a line and a circle which are intersecting. Now we know that such intersection points can be two. That means two intersecting circles in general intersect at 2 points. Similarly, a line and a circle also intersect generally at 2 points. However, sometimes it may be necessary to choose the correct point of intersection for the problem in hand. As I said, all these points will be shown very clearly when you solve those particular examples. The third point is, sometimes we may use a tracing paper as an overlay, and we will see that this will be very convenient, especially if there are higher order links present in any particular mechanism. And lastly, we must know that the graphical method of displacement analysis cannot be used unless there are adequate number of 4 links closed loops in that particular mechanism. Unless we have adequate number of 4 link closed loops, the graphical method of displacement analysis cannot proceed. So, let me start with the first example, which is a slotted lever quick return mechanism which are used in shaping machines. First, I will show you the model, then the kinematic diagram of the same mechanism, then pose the question of displacement analysis. This is the model of the quick return mechanism that is used in a shaping machine. This is the cutting tool. This tool holder moves in a slot in the frame of the machine. This is what is called the bull gear, which is rotated at a constant speed. And here is a block which is hinged to the bull gear, and this block moves up and down in this slotted lever, and the slotted lever is hinged to the frame at this point, and the slotted lever is connected to the tool holder by an additional link. So we have a 6-link mechanism here, where the continuous uniform rotation of the bull gear is converted into the to and fro motion of the cutting tool. Now, the cutting tool during the forward motion is doing useful work, and we have to maintain a proper cutting speed. However, during the return stroke of the tool, this is not doing any useful work, so I would like to make the return faster, and that is why it is called quick return mechanism. As is seen very clearly, if I rotate the bull gear at almost uniform speed, the forward motion is slow, but the return is faster. This is the kinematic diagram of that 6-link slotted lever mechanism, the model of which we have just seen. Here, this link O2A, that is link number 2, represents the bull gear. Link number 3 is the block which goes up and down in the slotted lever, which is link number 4. Link number 5 connects the slotted lever to the tool holder, which is represented by link 6. So we have a 6-link mechanism with a revolute pair at O2, revolute pair at O4, revolute pair at A, revolute pair at B, revolute pair at D. And there are 2 prismatic pairs, one between 1 and 6 in this horizontal direction, and there is a prismatic pair between link 3 and 4 along the slotted lever. The problem is, if link 2 rotates at a constant speed, say omega 2, then we have to find what we call, say, QRR, quick return ratio. By quick return ratio, we mean the time that the tool takes for the forward motion and ratio of the time taken for the forward motion and the backward motion. Now, if link 2 is rotating at a constant speed, say omega 2, then the time it takes for the forward motion is theta forward, that is the rotation of link 2 during the forward motion, and backward motion is theta, say return, theta r, where theta r is the rotation of link 2 during the return motion. So the problem is, given this mechanism, can we find the quick return ratio? Before I start solving the problem, let me restate the problem for your benefit. That is what we are taking as our example 1. Example 1 is determination of quick return ratio of a slotted lever mechanism used in shapers. It has already been seen that the quick return ratio, which is defined as QRR, is equal to theta f by theta r, where theta f is the rotation of link 2 during the forward motion and theta r is the rotation of the same link 2, that is the bull gear, during the return motion of the cutting tool. Of course, we are assuming that the angular speed of link 2 remains constant. Let us now return to the kinematic diagram of the same slotted lever quick return mechanism, in which link 2, that is this line O2A, represents the bull gear of the input link, and link 6, that is this block D at D, represents the tool holder or the cutting tool. As this bull gear rotates counterclockwise direction, this tool moves from right to left and left to right. This motion from right to left is the cutting motion and left to right is the return motion. Our objective is to determine the quick return ratio of this particular mechanism and also to determine what is the stroke length of the tool. To analyze the problem, let me first note that this point A moves along this circle whose center is at O2 and the radius is O2A. That is, this circle represents the path of the point A, and I call it KA. To locate the extreme positions of the slotted lever, that is this link 4, I draw a tangent, two tangents from the point O4 to this circle KA. This is the tangent to the right, and similarly this is the tangent to the left. Consequently, the rightmost position of the slotted lever, that is link 4, is represented by this line, and the leftmost extreme position of the same slotted lever O4B is represented by this line. When the slotted lever along these two lines, the point A is at this location, let me call it AR, and at this position, let me call it AL. Since the distance O4B does not change, so I can also locate the rightmost position of the revolute pair at B by taking this, drawing this circular arc with O4 as center and O4B as radius. So I get this point, which I call BR, denoting the rightmost position of B. The same way, on this line AL, O4AL, I locate the leftmost position of the revolute pair BL. Now let us notice that the point D is going along this horizontal straight line, and the distance BD does not change. So when B occupies BR, let me locate where is DR. To do that, I draw a circular arc with BR as center and BD as radius, which intersects this horizontal line, that is the line of stroke of the cutting tool, at this point, which I mark as DR. So DR indicates the extreme rightmost position of link 6. The same way, I can locate DL on the same horizontal line. This is the line of movement of D, and D does not change, BL is here, so I draw a circular arc with BL as center and BD as radius to locate the extreme position of the point D, which I call DL. So this distance DL-DR represents the stroke of the cutting tool according to the scale of the figure. Now to find the quick return ratio, what we see that the link O2A rotates from O2AR to O2AL during the forward movement. So this is the angle through which link 2 is rotating through its forward movement, which I call theta f. Same way, during the return motion, the point A is going from AL to AR, that is link O2A is going from O2AL to O2AR and rotating through an angle which I call theta r. So you can easily determine the quick return ratio Q R R as the ratio of the angles theta f divided by theta r. So we have solved the problem. We have determined for this given slotted lever quick return mechanism the quick return ratio given by theta f by theta r and the stroke of the tool as dr dl for the particular given mechanism. We can also note that if the stroke length dr dl has to be decreased, then I have to change the length O2A. And as we decrease the length O2A, the distance dr dl will change, that is the stroke length of the tool will be decreased. However, as we decrease the radius O2A, then this tangent from O4 to this circle KA, that is these points AR and AL, move upward, and the angle theta F and theta R both tend to the value 180 degree. Consequently, QRR, which is theta F by theta R, when both of them tend to same value 180 degree, QRR reduces. That is, this mechanism is okay for producing quick return effect so long the stroke of the tool is sufficiently large and the quick return effect continuously decreases as the stroke length of the tool decreases. We have just now explained that the slotted lever quick return mechanism used for shaping machines is not good for smaller stroke length, because then the quick return ratio tends to become 1. That is, the quick return ratio decreases with decreasing stroke length. However, for slotting machine where the stroke lengths are normally short, we have to have a different types of quick return mechanism where the quick return ratio is independent of the stroke length. Such a mechanism is called Whitworth quick return mechanism. So, we shall see first the model of such a Whitworth quick return mechanism, then pose the same problem as example 2, determine the quick return ratio of this Whitworth quick return mechanism, and also see that how is it independent of the stroke length of the tool. So, before showing you the model and solving the problem, let me restate the problem for your benefit. This is our example 2, that is determination of quick return ratio of Whitworth quick return mechanism used in slotting machines. As I have said earlier, we will also show that in this mechanism the quick return ratio will be independent of the stroke length. This is the model of that Whitworth quick return mechanism. Here the cutting tool is this one, which is moving in this horizontal slot. So, if we rotate the input link at a constant speed, as is obvious that the forward and return motion of the tool is taking different time. It is going much faster on this direction and coming back much slower in this direction. So, if this we considered as the cutting tool which is cutting in that direction, then we should rotate it in the opposite direction. It is cutting slowly and returning much faster. Next, we shall see the kinematic diagram of this Whitworth quick return mechanism and analyze its quick return ratio. This is the kinematic diagram of that Whitworth quick return mechanism. As we see, this is also a 6-link mechanism with 5 revolute pairs and 2 prismatic pairs. This link 6 is the tool holder and link 2 is the input link which rotates at constant angular speed. Link 3 is the block which goes along link 4 at this prismatic pair. Link 4 is hinged to the fixed link at O4, link 2 is hinged to the fixed link at O2, and link 4 or 5 are connected by this revolute pair at C. Link 5 and 6 are connected by this revolute pair, and link 6 has a prismatic pair with fixed link 1 along this horizontal direction. For these given kinematic dimensions, our objective is to determine the quick return ratio if the link 2, that is the input link, rotate at constant angular speed. First thing to note that the stroke of the tool, that is this 6, is entirely decided by the length O4C. When D goes to the rightmost position in this direction, C comes on this line. O4C and CD becomes collinear. Similarly, for the leftmost position of this link 6, again O4C and CD becomes collinear, but C comes on this side on the line O4D. And the stroke length of the tool is obviously equal to twice of O4C, because the maximum distance is O4C plus CD and the minimum distance is CD minus O4C. So, the total movement of the tool is given by twice O4C. That is, the stroke length is changed by changing the length O4C. No change is made in the length O2A. Whereas, as we shall see, that the quick return ratio will be entirely decided by the link length O2A, the position of O2 and the position of this horizontal line. This is the kinematic diagram of the same Whitworth quick return mechanism which we have just seen. This link O2A is the input link number 2, and this link 6 is the output link, that is the tool holder. Due to continuous uniform rotation of this input link 2, this tool holder 6 oscillates along this horizontal line. Now, the point to note is this point A moves on a circle with O2 as center and O2A as the radius. This is the path of the point A. Let me call it KA. Again, we should note that the points A, O4 and C always lie on the same straight line, and O4 is never moving. So, when the point A comes here, that is the point of intersection of KA and the line of reciprocation of the tool, let me call this point of intersection is AL. Corresponding to this position of A, since A, O4 and C are always on one line, C will be also on this horizontal line and at a distance O4C from O4, because this is also a link length which is not changing. Corresponding position of C, as C moves on this circle with O4 as center and O4C as radius. So, this point I will call CL. That is the leftmost position of C. Correspondingly, D will move here such that CLDL is CD, because this link length is also not changing. So, this is the leftmost position of the tool holder. Let me call it DL. Exactly the same way, when the point A occupies this point, which is the intersection of KA and the line of reciprocation of the tool through O4, let me call this point of intersection as AR. Since C is moving on this circle and A, O4 and C must be on one line, if I draw this circle, that is the path of C, when it intersects this line of reciprocation, I will call that intersection as CR. Again, the distance CD is unique. So, from CR, if I draw an arc with CD as the radius, I get the rightmost position of D, which I call DR. Thus, this tool, that is this link 6, moves from DL to DR, that is the stroke length, which is exactly equal to 2 times O4C. However, during this movement from DL to DR, the point A goes from AL to AR, and from DR to DL, the point A goes from AR to AL. As we see, the O2A, this link is rotating with constant input speed. So, from right to left, the rotation is this angle, which I call theta f, and from left to right, it rotates only through this angle, which is 2 pi minus theta f. That is, during the return stroke, theta r is 2 pi minus theta f, and the quick return ratio is theta f by theta r. As we see, the stroke length can be changed by changing the length O4C, which has no role to play so far as these two lines are concerned, that is O2AL and O2AR. That is decided by the intersection of the circle KA and the line of reciprocation of this point D. So, the quick return ratio remains same even if we change the link length O4C, which causes a change in the stroke length. So this is the quick return ratio of the Whitworth quick return mechanism, which is independent of the stroke length. As our next example, let us consider another 6-link mechanism which is shown in this figure. Here, as we see, there is a 4-bar mechanism O2 A B O4. Link 4 of this 4-link mechanism, that is this link, is connected to another link 5 at this compound hinge B, where 3 links are connected, namely 3, 4 and 5. Link 5 is connected to the slider, which is link 6, and slider has a prismatic pair with the fixed link such that the point D moves in the horizontal direction. The question is, if this link O2A, that is link number 2, rotates completely, what is the stroke length of the slider at D? The scale of the diagram has been shown here, that this distance is equal to 5 cm. Now for this problem, first we have to see that the 4-link mechanism O2ABO4 happens to be a crank rocker, because the maximum link length O2A4, which I may call L1, that is L max, and L2 is L min, and L max plus L min is less than L3 plus L4, that is the other 2 link lengths. So this is a Grashof linkage with O2A as the shortest link. Consequently, this link O2A will rotate completely. We have to find out what is the maximum rightmost position of this point D and what is the leftmost position of this point D, such that I can determine, say, DL and DR, which will give you the stroke length of the slider 6. Before we solve this problem, let me write out this problem for your benefit. This is our 3rd example, and example 3 is, the figure shows a 6-link mechanism. Determine the stroke length of the output link, that is the slider 6. Also determine the quick return ratio assuming constant angular speed of link 2. Let us now solve this example 3, and the kinematic diagram of that mechanism is shown here again. The problem is first to find the stroke length of this link 6, that is the slider at D. To find the extreme right position of the point D, first we have to find out what is the extreme right position of this point B. Due to this length O4B, that is link 4, B moves on a circle with O4 as center and O4B as radius. This circle represents the path of B. Let me call it KB. Now the extreme right position of the point B will be taken up, as we have discussed earlier, when link 2, that is O2A, and link 3, that is AB, become collinear. So the extreme position of B, let me call it BR, when O2BR is equal to O2A plus AB. So I take O2A plus AB, and from O2 I mark that distance at BR. Let me repeat, B moves on this circle, and at the extreme position O2A and AB become collinear, so O2BR becomes O2A plus AB. Similarly, for the extreme left position, again link 2 and link 3 become collinear, but O2A comes here, let me call it AL, and ALBL. This ALBL is equal to AB, and that becomes, this point becomes BL. That is, O2BL becomes the difference of the link lengths AB minus O2A. So I take the difference of O2 AB and O2 A and take that from O2 and mark it on KB. So the link 4 oscillates from O2 BR to O2 BL. So this is a crank rocker mechanism, and this is the rocking movement of link 4. Now BD is of fixed length and D moves on this horizontal line. So from this BR, if I mark, this is BD, from BR I mark this circle, and wherever it intersects the horizontal line through D, that determines the extreme position of D. I call it DR. Similarly, from BL, again taking the same length BD, I draw a circular arc, and wherever it intersects this horizontal line through D, that determines the extreme left position of D, that is DL. So this distance DL DR determines the stroke length of this slider 6. Now to determine the quick return ratio, that is the time taken from left to right and right to left, I can find out, assuming of course that link 2 rotates at uniform speed. For BR, the corresponding point of A, this is the circle on which A moves, with O2 as center and O2A as radius, which we call KA. So for the extreme right position, A comes here, let me call it AR, and for the extreme left position, that is BL, this point is which we have already marked as AL. As the link rotates uniformly from right to left, the rotation of O2A is given by this angle, that is the angle between O2AR and O2AL. And from left to right, the rotation of the same link 2 is given by this angle, that is 2 pi minus this. So if I call from right to left, that is the forward motion is theta f and the return motion is theta r. Of course, theta r is nothing but 2 pi minus theta f, and QRR, the quick return ratio of this mechanism, we obtain as theta f by theta r. Let me now summarize what we have learned today. We have done the graphical method of displacement analysis and have discussed 3 different examples of 6-link mechanism to show how graphically we can determine the quick return ratio or stroke length once the kinematic dimensions of those mechanisms are given. We started with a slotted lever quick return mechanism used in shaper machines, where we saw that the quick return ratio depends on the stroke length. Then we discussed the Whitworth quick return mechanism, where the quick return effect is independent of the stroke length. And in the third example, we have seen how from a Grasshoff's crank rocker linkage we can again get a quick return mechanism by using 2 more extra links and converting it to a 6-link mechanism. We have also seen that whenever we need the point of intersection of a straight line and a circle, we have to choose the correct point of intersection. In our next lecture, we shall discuss a little more involved and difficult problems on displacement analysis.